Good afternoon. It is a pleasure for me and a great honor to introduce Professor Dusa McDuff from Barnard College, Columbia University. Dusa comes from a very interesting family, many interesting ancestors. The most interesting one for us is Professor C.H. Waddington, a remarkable biologist, geneticist. He was a predecessor and inspirer of René Thom's theory of catastrophes, and then he promoted it in many different ways. He promoted mathematical biology and more generally theoretical biology as a new subject of study. There is another ancestor, but it's still conjectural. We have to do check some documents before talking about him. Despite the influence of those ancestors, Dusa decided to be a mathematician at a very young age. And he started a career in mathematics. She did very well, even though she had obviously to face many of the obstacles that are present for women mathematicians to succeed. She succeeded, and in her autobiography, one of the teachers that she gives most important is Israel Gelfand, which with him she had a long contact. And her field of mathematics is symplectic geometry and symplectic topology. She has done absolutely marvelous work on these subjects that I cannot detail. It would take me half an hour at least to do it. And but I hope that she will let us learn some of her work in her talk. Thank you.
Thank you very much for that kind introduction. It is a wonderful opportunity for me to be in Mexico today. I've never visited Mexico City, and this is my first visit, so it's a wonderful, I've had a great tour of various places. Also, many congratulations on the 75 years of this institute, and I hope you have another many, many years of flourishing ahead of you. So my talk is going to be a very general talk. Let's see, does it work? Well, oh, there we are. So I'm going to give a very general talk about symplectic structures. I think they're a rather elusive geometric structure that can be put on an even dimensional space. Sorry, what happened? Oh. No, what's happening to this? Oh, perhaps I'm pressing the wrong one. So it turns out that this, although it's a geometric structure, it seems to be topological in nature as well as geometric. So I would like to try and explain that. I'm going to talk about some basic properties, some fundamental results, and briefly discuss some open problems. So here's a just rough outline. What is symplectic topology? Some fundamental results, and some open questions. So to begin with, talking just about geometry, so I'll start with a very familiar picture of Euclidean geometry, where you study angles, distance measure, and you can study circles. And here is a picture of some of the basic theorems in Euclidean, sort of features of Euclidean geometry, together with a picture of Euclid. Now, if you're doing it in general dimensions, then you use n coordinates, n real coordinates, and you describe the measurements, the lengths and angles, in terms of the dot product, which is this v dot w here, just as in 3 dimensions. It's just a sum of the products of the coordinates. And you get the length times the length of the two vectors times the cosine of the angle between them. And there's Pythagoras' theorem, which is, of course, very well known. And the important feature here is that the dot product is symmetric. So let's see here. So v dot v, if you have v dot v, w is the same as w dot v. So it doesn't matter. The order doesn't matter. So that's the basic structure in Euclidean geometry. Now, in symplectic geometry, you have a very similar structure, but instead of using the dot product, you replace it by this antisymmetric form, which I write as omega 0 of VW. And so it's antisymmetric, so it does matter the order. Omega 0 of VW is the negative minus omega 0 of WV. And so that means that when you measure, if you put V and V, you always have to get 0. So that means there's no analog of length, because if you have a single vector, you don't get any measurement. What you do get is if you have two different directions, then you do get something which you can think of as a signed area. So the properties of this measurement, it's non-degenerate. So that means that if you're given a non-zero vector, you can always find a W which pairs non-trivially with it. So it's non-degenerate, and you can only get that in an even-dimensional space. That's why it's an even-dimensional geometry. The next thing is it's a closed thing. So it's actually omega 0 is a closed two-form. So you write that saying is that its derivative is 0. And so what that means is if you integrate this form, if you take the area of a little piece of surface with boundary, then it only really depends on the boundary. So if you move the surface S to S prime, you get the same area. So that means that you get very flabby measurements. You're measuring areas of surfaces, but you can move the surfaces without changing the area, as long as you fix the boundary. Now, the standard measurement is given by the standard linear form omega 0, and here in Euclidean space, it's just dx wedge dy. It's an area form, so if you're given two vectors, it's basically given by the determinant of their coordinates, and that's just the area spanned by the two vectors. That's what you're measuring, and it's a signed area, so it depends on the order here. Now, in 4 dimensions, you have a similar thing, but you have a measurement for the first two coordinates, x1 and y1, and then you add a measurement for the second two coordinates, x2, y2. So you can think this is meant to be a picture of 4-dimensional space with a little piece of surface in it, there's S, and you can project it onto the x1, y1 plane and take that area here. That gives you the first, that's the first component here. And then you project it onto the other two coordinates, the x2, y2 directions, and you take the area there and you take the sum. So that's what the symplectic form measures. It's a sum of area forms. And it seems a very strange measurement, so I really want to try and explain to you why it's a natural thing to do, what you get out of it. But one thing to notice is that this is a very, the measurement depends very much on the direction. You see, if I had a S here, which it just depended on x1 and x2. It didn't depend on the y coordinates at all. Then when you projected it down to the x1, y1 plane, you just get a line, so it wouldn't have any area. And if you projected it onto the x2, y2 plane, it would again project to a line and have no area. So this would be a plane in 4 space which has no area. The form would vanish on it. On the other hand, there are plenty of other planes where you do have area. So it means that the geometry looks different in different directions. So it's very different from Euclidean geometry. In Euclidean geometry, all directions are the same. Any two-plane looks the same as any other two-plane. But in symplectic geometry, it's very different. You have some planes where the form vanishes. They're called Lagrangian. Some directions where the form is, it gives you a positive area, and some directions where it gives you a negative area. And if you're doing it in higher dimensions, in R6, you do exactly the same thing. You just divide the coordinates into pairs, x1, y1, x2, y2, x3, y3, and you just take a sum in each of these things. So that's what the measurement is. So that's a symplectic structure. And it's a strange structure, so I want to try and explain some of its properties. Well, if you have a general manifold, not just Euclidean space, then it's an even-dimensional manifold. Then you take a closed, non-degenerate two-form. So it's a two-form omega, it's closed, and it satisfies a non-degeneracy condition, which can be written like that. And one of the basic properties is if you're given a function on this manifold, then you get a flow. You get a function, gives you a vector field in a way I'll describe in a minute, and you integrate the vector field to get a flow. That's a one-parameter group of motions. And this flow preserves the symplectic form, and it also preserves the function you begin with. So that's a very special feature of this geometry. So to explain that, you take your function, you take its exterior derivative, dh. That's a one form. Just differentiate with respect to the x variables and put dx, and differentiate with respect to y variables and put dy. Then you get a vector field, which is called a symplectic gradient, which is a dual vector field. So you use omega 0 as a pairing, and you say that a vector field xh has a property that when you take omega 0 xh and you evaluate it at v, that's the same thing as evaluating this one form at v. So that's just a linear transformation getting you from a covector to a vector field. And then you integrate that vector field. You look at the flow, so the derivative of the flow is just this vector field. That's a one-parameter family of diffeomorphisms, and the claim is that that family of diffeomorphisms preserves the symplectic form. So here's an example. If you just take the quadratic function, the half of x squared plus y squared on R2 with a standard form, then dh is just x dx plus y dy. You do this transformation using omega. Remember, omega 0 is dx wedge dy. So if you corresponding to a dx, you get d by d, you get a d by dy, a minus d by dy, and corresponding to this dy, you get a d by dx. So you get this vector field. And this vector field generates a clockwise rotation which preserves the circle's h. So those are the two things. It preserves area and it preserves your function. Right? And these motions are called symplectomorphisms. They're diffeomorphisms which preserve the symplectic structure. And the thing is that on any symplectic manifold, there are lots of them because there are lots of functions. So you get lots of these structure-preserving diffeomorphisms, which is very different from Euclidean geometry. Okay, so then there are many, there are very standard ones. These are standard ones which preserve a function. But if you let this function depend on time, so h depends on a time variable, t, you can do exactly the same thing and get not a flow, but a path of diffeomorphisms, which gives you very much more general things. And that means you have many, many transformations that preserve this structure. So it means symplectic geometry is very flexible. It's a structure which you can move what you have in many ways. That's a sort of topological feature of it. So now let's give a little bit of history. So in the 19th century, this is when this geometry was first really discovered by Hamilton. And in classical mechanics, this flow describes the time evolution of a mechanical system that preserves energy. So h would be the energy function. If you're studying the flow of a system that preserves energy, then you can write it down as a flow, one of these functions, phi h. And so energy is conserved as the system evolves with time. And this is the picture due to William Hamilton, who is also the inventor of quaternions. And in the last talk, we were hearing about the Hamiltonian. Well, the Hamiltonian's the same Hamilton, though I must say I don't understand exactly how it was applied there. So it was a much more analytic application. I'm doing sort of geometry. But anyway, this is the basic system, energy-preserving systems. And it was, here's a picture of Hamilton, of stamp that Ireland produced to measure his anniversary. And another famous 19th century mathematician who used these ideas of Hamilton was Sonia Kovalevskaya, who studied spinning tops, which was another energy-preserving system. Here's a stamp of Sonia Kovalevskaya from Russia in 1951, just celebrating. So that's what people were doing, the kind of symplectic geometry people were doing in the 19th century. Now, if you think in the early 20th century, Birkhoff was very interested in dynamical systems, and he was looking at properties of area-preserving transformations of the plane. So those are symplectic transformations, because in 2 dimensions, a symplectic form is just an area form. And he proved his celebrated twist theorem, which I tried to illustrate here, that says that if you have an area-preserving map of the annulus that twists the 2 boundary components in different directions, so this boundary component is going round in that direction, and the inner boundary component is going round in the other direction, then the claim is that such a transformation has to have at least 2 fixed points. So here are my fixed points, and I've tried to describe how the flow sort of goes around them. Of course, there could be more, but there have to be at least 2. And if it's area preserving, I mean, if it doesn't preserve area, it's very easy to see this is not true. And it also, if it doesn't satisfy the twist condition, it's not true. But this has been a great inspiration to more modern symplectic geometries, because this is what happens in 2 dimensions. And so then you ask, well, what happens in 4 dimensions? What happens in 6 dimensions? What's the analog of this theorem? OK, so that's one basic theorem. And another basic theorem is due to Moser, saying that if you have a 1-parameter family of symplectic structures on a closed manifold, so omega t, t is the time variable, you have a 1-parameter family, and you ask that the cohomology class, the de Rham class of this form, is constant. Then the claim is that all these forms are essentially the same, so there's a family of diffeomorphisms of the manifold which start at the identity and which pull back at the time t, omega phi t pulls back the form omega t to omega 0. So that's another classical theorem about symplectic geometry. And what it tells you is that if you start off with a form omega 0 and you try and deform it, you try and move it to some new structure, like if you had a Riemannian manifold and you took a metric and you tried to deform it. In a Riemannian case, or many geometric problems, there'd be an interesting deformation theory. But here, what you're saying is there's no deformation theory. As long as you keep the cohomology class the same, then you don't get anything new. It's just changing by a diffeomorphism. So those are, so that's telling you you don't have an interesting deformation theory. So then the question is, if you're given a manifold and you're given with a symplectic structure, what other symplectic structures does it have? And you can't get at it by local deformations. I mean, you can change the cohomology class, but that's a sort of uninteresting change. OK, so what happened more recently? That was sort of early 20th century. So later on in the 20th century, it was noticed that there are very deep and subtle connections between, between symplectic and complex geometry. And these were first noticed and exploited by Misha Gromov. So, symplectic geometry happens in even dimensions. And complex geometry also happens in even real dimensions, right? Because you've got the complex numbers is even dimensional. And so here's some pictures. Here's Gromov, and here's Fleur, I'll mention in a minute. And so what Gromov did in 1985 gave rise to a main tool in the modern theory, which is J-holomorphic curves, and I'll say a little bit more about that later. But that's what I've been using mostly. I mean, I got into the subject a little bit before Gromov did this work, but when he did this work, it was so interesting that I just started working with it. It was a very interesting new idea. And Fleur is a second figure here. He extended Gromov's ideas, using them to develop a version of Morse theory on the loop space, for spaces of loops and paths in a symplectic manifold. And that's now called Fleur homology. And that's incredibly influential, that theory. It comes everywhere in symplectic geometry. And so these are the basis. These ideas here are the basis of the relevance of symplectic geometry to string theory and mirror symmetry, about which I will say, this is what I'm going to say about it. I'm not going to say anything, right? Because I don't really know. This is not the area I work in. But it's why a lot of people are interested in symplectic geometry, because of these connections. So let me explain a little bit about the relation of symplectic and complex geometry. So we think of the plane, R2, and we identify it with the complex numbers where we have a complex variable z is x plus iy. So here are our two coordinates which are related by, in the symplectic form. And so we think of R2n, it's Cn. And then the symplectic form here, given by these pairs of things, which is, it's the length of v times the length of w times the sine of the angle between these, because it's an area. That's the same as the dot product between iv dot w. If you think of these as vectors in the complex plane, and I is multiplication by the square root of -1. So that's the immediate sort of relation. Here's a picture. Here's v and w, and our symplectic form is this area, and that's the dot product between iv and w. Right. And well, Gromov realized that you know, this was what happens in Euclidean space, where you have a multiplication. You've got this multiplication by the square root of -1. But he said, okay, let's look at a more generalize this operator here. So to make an operator called J, which is a generalization of this operator, multiply tangent vectors by I. So this is an operator which takes v to jv. These are tangent vectors. But the basic point is that when you square it, you get minus the identity. So it's like I squared is minus the identity. And it's also meant to be positively related to the symplectic form. So if you take the form and you evaluate it on a pair of vectors v, jv, it's always actually strictly bigger than 0. I should have put a strictly bigger than 0 if v is not 0. If v is 0, it could be 0. But those are the basic conditions for this operator j, that its square is minus the identity, and it's what's called tamed by the symplectic form. So here's an idea. Here's v, here's jv, and then j squared of v is minus v. And it's called a tame, almost complex structure. And the point is that every symplectic manifold has a contractible family of these things. So what's a J-holomorphic curve? Well, they're basically the analog in of symplectic geometry of geodesics. So, you could make this very precise, actually. But you know, that's what you should think of. In Riemannian geometry, you have paths of shortest length. Here are paths, instead of being one-dimensional, two-dimensional, and they're J-holomorphic. So they're one-dimensional complex curves, which therefore have two real dimensions. And so they look something like this. And so you think of them as real surfaces, C, such that for every vector v tangent to C, the vector jv is also tangent to C, that the tangent plane is invariant under this operator. That's what a J-holomorphic curve is. And typically, you parameterize it, so it's parameterized. So if in the complex plane, if you have, I mean, it's exactly what Jack Milner was talking about. If you take a polynomial in the complex variable z1, z2, and look at the solution set, then you get a J-holomorphic curve with a standard J. But you know, J is a much more flexible operator than the complex structure I. I is very rigid. J, you're just saying what it does at each point in the tangent space. So that means there are many more J-holomorphic curves than complex curves. And actually, there are many very interesting questions if you look in, you know, if you think in CP2's complex projective plane, and you look at a tame, almost complex structure, and you try to understand what do, say, curves of degree 27 look like if they're J-holomorphic for some J, and compare them with complex curves of that degree. Are they essentially the same or not? Anyway, so let me, so that's one of the tools we use. So let me tell you some special features of symplectic geometry. Well, one absolutely basic theorem, which is from the 19th century, so I could have mentioned it earlier, but I didn't, is Darboux theorem, which tells you that all symplectic forms on any manifold are locally the same, locally diffeomorphic, so that they locally look like that structure I gave you in Euclidean space, which means that all the invariants you have are sort of global in nature. And then another basic thing I did say something about this is that it has sort of two aspects to it, this theory, because you have two kinds of submanifolds. You have sort of important submanifolds. You have symplectic submanifolds, which are where the restriction of the form is non-degenerate. So that would be like in complex geometry, and you look at a complex submanifold, that would be, and then you're generalizing that. But then another thing you can do is look at a Lagrangian submanifold. So these are manifolds of actually half the dimension. You're in 2n real dimensions. These are n real dimensional manifolds where the restriction of the form vanishes. And these have a relation to dynamics, real algebraic geometry, and various other things. And then another very important thing is there's a very close relation to physics, which from its beginnings in Hamiltonian dynamics in the 19th century to all the mirror symmetry and dualities today. And then sort of what I'm very interested in, the group of symplectomorphisms, these are the transformations that preserve the structure. It's an infinite dimensional group. So it's distinction from what Jack was talking about, the group of complex automorphisms of a complex projective space or something. That's a finite dimensional group. It's a Lie group, but it's finite dimensional. This group here of all the transformations that preserve the symplectic form is infinite dimensional because it contains all these maps for any function. And it's also, very interestingly, it's closed in the C0. That's a uniform topology among all diffeomorphisms. So this is a topology that just measures the distance between the image points. It doesn't measure anything to do with derivative. It's not the C1 topology, it's a C0 topology. And this fact here, which I'll say a little bit more about later, is why we can talk about symplectic topology rather than symplectic geometry, because really the basis of the theory does not involve derivatives. Even though we're talking about one-forms which live on the tangent space, somehow there's some basic part of the theory which we don't completely understand, but it depends just on topology. And so there's this, I'll say more about this, but there's a notion of a symplectic capacity, and using that, you can characterize when a diffeomorphism preserves the symplectic form without involving any derivatives. I mean, normally you're saying that the derivative of phi preserves omega, so that involves derivatives. But there's a way of explaining this without using derivatives. And so this is what I said, that symplectic geometry is basically a topological theory. And one of its features is that it has a very interesting interplay between flexibility and rigidity. So flexibility means that you can sort of do anything that's obviously not impossible. And rigidity means that sometimes there are things are impossible for no good reason, or reasons we don't completely understand. And there's a very interesting, which again, the demarcation between this regime and that regime is not well understood. So that's a sort of general slide. So let me tell you some fundamental results. So move on to the second part of the talk. So let's just say a little bit in 2 dimensions. So in 2 dimensions, whoopsie, we can go back. In 2 dimensions, a symplectic form is an area form. And so that means that every closed-oriented surface, an area involves having a surface, has a natural symplectic structure, which is unique up to a scaling factor. So the existence problem is not difficult. We know exactly what we have. And there are many area-preserving diffeomorphisms. And so here's another nice theorem of Moser from the same paper, another classical theorem. It says if you have a closed disk in the plane, and it's diffeomorphic to a closed region of the same total area. So here's the disk, and here's a region with the same total area. Then there's a diffeomorphism between them. Then the claim is you can find an area-preserving diffeomorphism phi, which takes from D to U. So that, in other words, there's a symplectic transformation that takes D to U. So that means there's no interesting invariance. For a region in the plane, if you know what its topology is, and you know its total area, then you know everything that symplectic geometry can tell you. So in higher dimensions, of course, the situation is quite different, and we don't understand it. So that, this is the 2-dimensional picture, and we're interested in what the higher dimensional picture is. So this is one of the first fundamental results of Gromov, called the non-squeezing theorem. And what it says is this. We're looking at an analog of that 4-dimensional, the 2-dimensional problem was taking a disk and mapping it into some other region in the plane. So here we take a ball, which is B4A. It's a 4-ball. I'm just restricting to 4 dimensions. It could be any dimension. So these are two complex coordinates, and we say that pi times the sum of the first length squared plus the sum of the second length squared is less than or equal to A. So that's a ball in R4 or C2. And A is a measurement of area, because that's a sort of natural measurement, because it's a 2-dimensional measurement. So A is the area of a slice. If you take a 2-dimensional slice through it, that's what you'll get. And so we're trying to embed that ball into a cylinder. So the cylinder is a product of a disk in the first 2 dimensions. This is a disk in the first 2 dimensions times R2 in the other direction. So we've only got restrictions here on the first area. And we're trying to say, can we take this ball and embed it into the cylinder, of course, in such a way as to preserve the symplectic form. So we want a symplectic embedding here. And the non-squeezing theorem of Gromov showed that you can do this only if the ball, A, the area here, is less than or equal to the width of the cylinder. So all you can do is basically just include it in by this obvious inclusion map. There's no cunning way you can twist it around in order to embed it. So that was his amazing theorem. And the thing is that this theorem actually works in all dimensions. It's one of the few embedding results that works in all dimensions. You take a ball in dimension 2n. The cylinder would again be, though, a 2-dimensional disk times a large dimensional Euclidean space. So there's the symplectic analogs in all dimensions, but it's not true in the volume-preserving case, because in the volume-preserving case, you can squeeze in the first 2 directions with lambda and compensate by multiplying in the second 2 directions, and that will get you an volume-preserving map from the ball into the cylinder. So it's very much a symplectic result, this. Now, you look at this and you think it might be just a curiosity. It may be, okay, that's interesting. But in fact, this result is, oh dear, it's going forward. This is a cornerstone of the modern theory. It's an absolutely fundamental result. So let me explain why. So this work is due to Gromov and Eli Ashberg, also I didn't mention him, Ekeler and Hofer. So if you're given an open subset of Euclidean space, define something we call the Gromov width Cu, which is a supremum of the sizes of balls that embed symplectically in U. So that's a measure of the size of U, which is symplectically invariant. So if U is symplectomorphic as a symplectomorphism from U to V, you get the same answer. And it's also monotone. So if U is sitting inside V, then the size of U is less than or equal to the size of V. So it's a monotone symplectic invariant, and it's also somehow essentially 2-dimensional. In other words, if you take a ball of area A, this is a cylinder, a 2-disk, times Euclidean space, that's got infinite volume, but it's got finite capacity, because the largest size of a ball, by the non-squeezing theorem, the largest ball you can embed in here has got size big A. So it's got finite capacity. So you've got a measurement of a size which is a 2-dimensional measurement, which is symplectically invariant. And the theorem is that if you take an orientation-preserving diffeomorphism that preserves this capacity, in other words, just a diffeomorphism, a local diffeomorphism of Euclidean space, such that for every open set, the capacity of the image of U is the same as the capacity of U, then that map preserves a symplectic form up to sign. There's some little sign discrepancy which you can compensate for. So that's a way of describing, and this thing about preserving capacity, you can prove depends only on, it's a C0 measure. It doesn't involve first derivatives. So this is the way you can describe symplectomorphism, symplectic geometry, just using C0 information. And so, there are many functions that you can play these roles. I mean, there's a certain set of axioms, there's basically that you axiomatize this condition here. There are many, many measurements you can make, and there's a whole wealth of people who've done very interesting work defining measurements of this kind. Yeah, okay, so I should go back a little bit. Just go back, if I can go back. Yeah, oh, what happened now? Yeah, here we are. So, you know, this is a very fundamental fact, though, that you had, and this theorem here leads to the existence of symplectic topology, and I'll say a little bit about that later. What I was going on to now was to talk about some problem that I've actually worked on fairly recently, which is a problem about looking in 4 dimensions, but instead of trying to embed balls in other shapes, let's try and embed ellipsoids into ellipsoids. So here, this is a picture of Helmut Hofer, who did a lot of work on this and was very interested in this question. And so the question is, you look at an ellipsoid EAB, which is just in 4 dimensions. So it's, again, it's pi times z1 squared over a plus z2 squared over b less or equal to 1. So if A is equal to B, you have a ball, but if A is different from B, you get some kind of ellipsoidal shape. And, you know, there's a theorem that tells you if you take any ellipsoid, any quadratic form, positive definite quadratic form, and you look at the set of points where that quadratic form is less or equal to 1, you can always put it by a symplectomorphism in this form. So this is the most general ellipsoid in symplectic geometry. And then the question is, when does one ellipsoid embed symplectically into another? And Helmut Hofer conjectured around 210 that the interior of one ellipsoid embeds symplectically in another ellipsoid if and only if certain numerical condition holds. This is a numerical condition, which I'll explain in a second. It's purely numerical. And so what is it? Well, you take the set of numbers k times a plus l times b, where k and l are integers, non-negative, and you arrange this set of numbers with multiplicities in increasing order. So, for example, if you take a and b to equal 2, both equal to 2, then you have 0 when l and m is 0. You get 2 twice because you can either take a or b. So you can take 1 times a and 0 times b, or 0 times a and 1 times b. So that's 2, 2. You have 3 ways of getting 4, because there's twice a, there's a plus b, and there's twice b. And then there's 4 ways of getting 6, 5 ways of getting 8, and so on. So that's a set of numbers. And you compare it with this set of numbers, n1, 4, where you do exactly the same thing, but you have 0, and then you have 1, 2, 3, 4, but you can get 4 twice. And then you can get 5 twice, because you can have 5 times 1, or you can have 1 plus 4, and 6 twice, 7 twice, 8 3 times, and so on. So that's just a set of numbers. And the claim is that, you know, if this set of numbers, here for 2, 2 is, you can prove very easily it's point-wise bigger than or equal to that set of numbers. Right? So that's this condition. So that tells you then, if Hofer's conjecture is true, that the ellipsoid 1, 4 should embed, the open ellipsoid should embed in the ball 2, 2. Even though you can't sort of see an explicit embedding, there should be one. That's what the condition says. So this is one of the things that I actually proved. And here's an illustration of what it means. So let's look at, you know, people are interested in trying to define the capacity function. If you're looking at the ellipsoid into ball embedding problem, you're looking at trying to embed, I should have said, the interior of this ellipse, E1a, so you normalize the first one to be A1 and the second to be A, bigger than 1. And you want to embed it in a ball, and you take the infimum of the balls you can embed it in. And that gives you a function, C of A. So C of A just measures the smallest ball for which this embedding happens. And this is a perfectly well-defined function, and you can ask what it looks like. And so I calculated this with Schlenk in 2012, and it has this rather surprising structure. In other words, you'd think it's obviously increasing. You'd think it would be just sort of vaguely increasing. But it's actually got a very, very well-defined structure. And so if this number a is less than tau to the 4th, where tau is the golden ratio, so it's about 6, this number is roughly 6.7, so somewhere there. then you have an infinite staircase with numerics based on the Fibonacci numbers. So you go straight up. So here the function CA is equal to A. Then the function's constant for a while. And then you go up again, and then it's constant. You go up, and it's constant infinitely many times. And all these points here, those points are all described by certain things to do with the Fibonacci numbers. And what's interesting, if you're trying to think of flexibility and rigidity, means that if A is in between 1 and 2, you have a completely rigid problem. You have an ellipsoid, and all you can do, if you're trying to embed E1A into this thing, well, mu has to equal A. So there's no bending. You just have to include it. It's absolutely rigid. But as soon as A gets to be 2, well, I mean, this actually, the fact that this is 2 was something known to Hofer, that it was completely rigid there. But the fact that you could then, it was completely flexible here. So the only obstruction is volume, was a surprise, right? So this shows the distinction between flexibility and rigidity, that you have some places it's rigid, you can't do anything, rigid there and flexible there, rigid, flexible, and so on. And so that's this very rigid part of it. Then we have, when A is big enough, so bigger than 17 over 6 squared, then this capacity is just the square root. And the square root is given by the volume, you see, because the volume of the ellipsoid, E1A is just A up to some factors of pi. It's A over 2 or something. And the volume of this then is mu squared over 2. So then if this embeds in that, mu squared over 2 has got to be bigger than A over 2. So that means that A's got to be, that CA has to be bigger than or equal to its square root. So that's a lower bound coming from volume. And so eventually, when A is big enough, it's completely flexible. And then in between here, we have some region, a transitional region, where sometimes there's a constraint and sometimes there isn't. So, this is a very, very precise, whoopsie, a very, very, can I go backwards? Backwards. Very precise result, there are some other very precise functions worked out for similar problems like this. But, if we try and go beyond dimension 4 is always special. If you try and go beyond dimension 4, then we don't really know very much, except that there's an obvious analog of Hofer's conjecture, because Hofer's conjecture was this question, you took this sequence of numbers here, NAB, and you were saying that you have an embedding if this sequence of numbers is less than or equal to that sequence of numbers. Well, if you had 3 numbers, A, B, C, and D, E, F, you could do a similar sequence of numbers, just taking KA plus LB plus NC. You could have a similar sequence of numbers and say there's an embedding if and only if that sequence of numbers is less than that sequence of numbers. And one thing is we do know that that's not true. So, that we have no results, but we do have a negative result, that Gut produced some embeddings to show that that's false. But there's a very interesting question, I think, about what actually happens in to this problem in dimension 6, dimension 8, and there are some results, but certainly we don't understand it completely. So now let's tell you some other questions that are open. So first of all, one very important question is which smooth manifolds do have symplectic structures? And there's some necessary topological conditions. So for one thing, you've got to have an almost complex structure. So not all manifolds do allow a J. So that's a topological condition. Not a terribly difficult one, but you certainly need that. Which is, you can think of it as a higher dimensional analog of an orientation. It's some structure on the tangent bundle. And if the manifold's closed, then we're compact without boundary, then you have a cohomology class A, which is represented by the form, whose nth power has got to be positive. So that's another topological constraint. But those are the only 2 topological constraints we have. Now, what Gromov showed was that if M is connected and open, so it's non-compact without boundary, then that's enough, that if it's got an almost complex structure, you don't even need a cohomology class. It has a symplectic form. If you take closed manifolds, then the only result we have is in dimension 4 due to Taubes, which tells you that there are 4-dimensional manifolds which satisfy these two conditions here, but do not have a symplectic structure. So if you take the connected sum of 3 copies of CP2, then you can show it satisfies the conditions, and then using gauge theory, you can show it doesn't have a symplectic structure. And so it seems very unlikely that these conditions are enough in higher dimensions, but we don't have any proof. We don't have any examples. We don't have any analog of Taubes' theorem in dimension 6, because all our methods are sort of 4-dimensional methods. So that's a nice question, but it's very hard, I think. So now there's analogous questions in contact geometry. Contact geometry is the odd-dimensional version of symplectic geometry. And these questions now have some answers. So let me explain that, because that's a very recent development that's sort of interesting. So let me first of all say a little bit about contact geometry. So a contact structure on a manifold, this is now an odd-dimensional manifold. It's given by a nowhere integrable hyperplane field psi. So that means if it's a manifold of dimension 2n plus 1, then these hyperplanes have got dimension 2n. And so it's given by the kernel, locally anyway, given by the vanishing locus of a 1 form. It's just the kernel of some 1 form. And to say it's non-integrable, it means that the planes that you have are always twisting. So here is meant to be an illustration of an example in R3. The planes you start off with is meant to be symmetric, but under translation with an axis perpendicular to this disk. And as you go out along a radius, you start off in the center, it's horizontal, and then it twists uniformly. And that twisting means that it's non-integrable. It means that non-integrable means that, in 3 dimensions, it means that there's at no point is there a 2-dimensional surface which is tangent locally to this plane field. So the curvature of the plane field is always non-zero. And so it means then the curvature of the plane field, which Danish actually describes as symplectic structure, if you take this odd-dimensional manifold and multiply it by a little interval, you get an even-dimensional manifold, and that has a natural symplectic structure. So that's a relation. So that's a contact structure. And if you have if you take a sphere, say, in R2n, if it's a convex hypersurface, then it has a natural contact structure. So there's a sort of relation between symplectic and contact geometry in that way. And so some aspects of the geometries are the same and some are different. So in both geometries, if you have a function on a manifold, then it generates a flow that preserves the structure. So that's what I told you about in the symplectic case, and it's also true in the contact case. But the squeezing phenomena are very different, because the contact structure in Euclidean space, there's also a Darboux theorem, which tells you that all contact structures are locally the same. So you can sort of for local information, you can look at Euclidean space. And you have always a rescaling transformation, which multiplies in 2 directions by lambda and in the 3rd direction by lambda squared. If the form is written correctly. I didn't write down what the form looks like. But anyway, it means there are still some non-squeezing phenomena, but they're very different. I don't want to explain them, but they just look different. Anyway, so what was recently done, these are 3, this is Strom-Bormann, Yasha Eli-Ashberg, and Emmy Murphy, recently showed that if you have a hyperplane field on a manifold that satisfies a very mild topological condition, then it can be homotoped to a contact structure that's unique up to contactomorphism. So that gives you a very powerful existence theorem. That almost any manifold, this condition is more or less that it's just a tangent bundle condition. It's a very minimal kind of condition. So it means you have lots and lots of contact structures. It solves the existence questions. But the trouble with this theorem is that all the contact structures you construct in this way are what's called over-twisted, which means if you look at their geometry, it means that there's certain 2-dimensional, well, it means there's a certain, people are still trying to understand exactly what it means, but there's a certain kind of local structure in the manifold that just means that it's very bad from many points of view. And one of the ways it's bad is that if you have a contact structure, which is, you know, it's a convex hypersurface which bounds a symplectic manifold, then the contact structure on such a boundary, like the standard contact structure on Euclidean, on the three-sphere, they're never over-twisted. They're always what are called tight. So from a symplectic geometer's point of view, all the contact structures that are interesting are not over-twisted. They're tight rather than over-twisted. So you get a whole lot of structures, but they're sort of, these structures are sort of uninteresting ones. It's the same in dimension 3. Eli Ashberg proved a long time ago that there's a notion of over-twisted, which is quite easily understood geometrically. And again, any closed three-manifold has an over-twisted contact structure. In fact, lots of over-twisted contact structures. But they're not interesting. There's a finite number. You know, not every three-manifold has a tight one. And any three-manifold has at most a finite number of tight structures. So there's a much more interesting geometric information comes from these tight ones, these rigid ones. It's rather like in foliation theory. There's a notion of a taut foliation, which gives you geometric information, taut codimension 1 foliation, while standard foliations give you very little information. So then we don't know anything about the existence and classification of tight structures. Well, I mean, we know quite a lot, but we don't really, and we know a lot in dimension 3, but rather little in dimensions higher than 3. So this question here is sort of like where we are with the existence of symplectic structures. That the symplectic structure is like a tight contact structure. So anyway, that's very exciting work, and there's a lot of good work going on about, what exactly does tight and over-twisted mean, and lots of interesting questions this has given rise to. But let me just finish with a few more questions. So this question is about sort of symplectic homeomorphism. So this is a topological part of symplectic geometry. So if we have a homeomorphism, so it's just a one-to-one map, which local one-to-one, let's say local homeomorphism, it's a local one-to-one map which is surjective and has an inverse, continuous inverse, and it's called symplectic if it preserves orientation and some kind of symplectic capacity, like the Gromov width. So that's what you mean by a symplectic homeomorphism. And so we are beginning to understand the properties of these homeomorphisms. So, for example, it seems that they preserve symplectic phenomena that are rigid. So they preserve Lagrangian submanifolds. So what that means is that if you have a symplectic homeomorphism, and you have a Lagrangian submanifold, so a symplectic homeomorphism, say, of Euclidean space, or some smooth manifold, and you have a smooth Lagrangian manifold, and it happens that the image of that Lagrangian manifold is actually smooth under this homeomorphism. Then that smooth image of the Lagrangian manifold under this symplectic homeomorphism is also Lagrangian. So you don't directly preserve the symplectic structure, but you do preserve this Lagrangian property. And it doesn't preserve properties that are flexible. For example, if you look at a submanifold which is symplectic, has codimension bigger than or equal to 4, there's a theorem of Gromov telling you that these things obey an H-principle. Submanifolds of codimension 4 are just flexible. They're not rigid, they're flexible, according to Gromov. And the work of Buchowski, Humilier, Leclerc, and Upstein, and Sefardini recently showed that that there are, this kind of flexible phenomena is not preserved, while phenomena like the existence of these Lagrangian submanifolds are preserved. So we have some results like that. But there are many, many interesting questions. Here's one which is very intriguing. Suppose you take the four-sphere. Can you give it the structure of a topological symplectic manifold? So, it doesn't have any two-dimensional cohomology, so it certainly can't be a smooth symplectic manifold, but conceivably, well, we don't know. Conceivably, it could be a topological symplectic manifold. In other words, you can find local charts where the diffeomorphisms, or the homeomorphisms, the transition functions are symplectic. So we just don't know that. So there are lots and lots of questions of that kind. So then here's another kind of question. I'm not thinking about these things, but I think they're very interesting questions. Here's another kind of question that I am interested in. So, you know, this is in dimension 4. I was telling you about looking about the ellipsoidal symplectic capacity function. This was looking at mapping ellipsoids into balls, and you look at the smallest ball you can embed. So the numerics of the staircase you get is given by the Fibonacci sequence, and it turns out that those numerics are very closely related to the numerics governing. There's an infinite number of distinct monotone Lagrangian tori in CP2 founded by Viana recently. So there's some, in Viana, there's this very, you know, you have the Lagrangian submanifolds. The interesting ones, the rigid ones are called monotone. That's it's just a homological condition on the Lagrangian. Those gives you the interesting ones. And there are infinitely many distinct monotone Lagrangian tori in CP2. And the numerics governing those are very close to the numerics of the Fibonacci staircase. And in fact, there is some relation between those problems. And you can say the underlying reason is the existence of certain almost toric vibrations. So then the question is, could there be a similar connection in higher dimensions? In both these cases, we do not understand, whoopsie, I didn't mean to do that. We don't understand what the 6-dimensional version of ellipsoid embedding capacity function is. We don't understand what tori there are in CP3, for example. And so, you know, it's conceivable that there's some relation between these problems. It's not just an accident in dimension 4. Anyway, that's a kind of question that seems interesting, that might get somewhere. So I think that's basically all I wanted to say. And now I have just a few references here, and there are lots of papers that I didn't give credit to everybody. Thank you for your attention.
Okay, questions?
So you mentioned the relation between complex geometry and symplectic geometry.
Mm-hmm.
And there is this place where the intersection is very complete, which is in Kähler geometry.
Right, right.
So in Kähler geometry, there are some beautiful theorems that you produce with the symplectic form, which are these Lefschetz, Hart-Lefschetz theorem.
Right.
There is this Hodge decomposition theorem,
Mm-hmm.
and then there's this Riemann-Hodge bilinear relations.
Right.
Is there a general framework in symplectic geometry where these theorems can be understood?
Well, the thing is that in symplectic geometry, the hard-Lefschetz theorem doesn't hold. So if you look at the cohomology of a general symplectic manifold, it doesn't have to satisfy the hard-Lefschetz theorem. So, these theorems do not immediately translate into symplectic geometry. You can't just take this as a packet and put them in symplectic geometry. I mean, that's a very interesting question, which I didn't mention here because I had nothing new to say about it. But what the relation is between Kähler geometry and symplectic geometry. Because the Kähler condition, you have a symplectic form, the Kähler form, but the J you're looking at is integrable, so it's very rigid. And in the symplectic geometry, you have a much more flexible J. And of course, the emphasis also is different, because in Kähler geometry, you usually fix the complex structure, and you let omega as a sort of afterthought, while in symplectic geometry, you fix omega, and then J is an afterthought. So there are very interesting relations, like you can look at uniruled, uniruled symplectic manifolds. There are uniruled Kähler manifolds where there's always a rational curve through every point, or some kind of rational divisor. There's a good analog of that condition in symplectic geometry. So then if you look at the question of whether it's rationally connected, so whether you're given 2 points, there's always a rational curve through them, there seems to be no good analog of that condition in symplectic geometry. I think Claire Voisin did some very interesting work on that question. And then there's general questions about positivity. Maury did all this wonderful stuff, the minimal model program in Kähler geometry. So what analogs are there in symplectic geometry? There is a monotone. If you look at a monotone symplectic manifold, what properties do they have? That's a sort of analog of a positive manifold. And we don't know. We don't have very many good results.
This homomorphism, symplectic homomorphism, given by capacity, can they be Z0 approximated by actual symplectic diffeomorphism? They are in the closure or no?
Not necessarily.
Not necessarily.
I mean, one thing you show is that if you have a sequence of diffeomorphisms which converges to a diffeomorphism in the C0 topology, then that diffeomorphism has to be symplectic. So
but
that's
if it's a
saying
homomorphism?
well, if you have it, that's saying that if you look at the group of symplectomorphisms in the C0 topology and look at the closure among all diffeomorphisms, then the group of symplectic diffeomorphisms is C0 closed. But I think, in dimension 2, I think it's true that any symplectic area-preserving any area-preserving transformation in dimension 2 is approximated by an smooth area-preserving diffeomorphism. In higher dimensions, it's presumably not true, but I don't know that anybody's really proven it.
Thank you.
Oh, what the numbers are?
Yeah.
Yes, well, in dimension 4, there's a very nice explanation of the numbers which Helmut gave. I didn't have time to explain. But there's a kind of homology theory called embedded contact homology, which is you look at the boundary of the ellipsoid, and because the ellipsoid is convex, that boundary has a contact structure. And you look at the Rabe flow. So a contact structure, if you're given a form, it always has a Rabe flow. So that's a particular flow on it, which is transverse to the contact direction. So on the standard contact structure in S3, it would just be the rotation around the great circles. So you have this flow on the boundary of a contact manifold. You look at the closed orbits under that flow and look at the actions of those orbits. So you look at a disk spanning them. And so these numbers are basically the actions. If you take There's a homology theory called embedded contact homology, where the cycles are given by positive sums of orbits. So you just take what these orbits are and you weight them. You take positive sums. And then the energy of that cycle is just given by the areas of the disks. And these numbers are precisely the areas of the disks corresponding to the ellipsoid. So they're basically action invariants in embedded contact homology, and there's some notion of an embedded contact homology capacities, ECH capacities, which actually quantifies this. So you're basically saying that one ellipsoid embeds in another if and only if the ECH capacities of one ellipsoid are less than or equal to the ECH capacities of the other one. So you're saying in that particular problem, the ECH capacities are a perfect invariant for the embedding problem. But you see, this contact homology is a particularly four-dimensional thing. So it doesn't, the embedded contact homology, it doesn't work in higher dimensions. So we don't have a similar, we have a much weaker theory in higher dimensions, which gives us the Ekelund-Hofer capacities. But that's not enough it's not a complete invariant for the problem.
About the same thing, I have a very simple question, maybe. Your condition seems to be an infinite. You have
it's an infinite condition, yeah.
Condition. There's no finite way.
Well, it's not. This set of numbers, it's hard to. I'm not an expert in how you do analyze a set of numbers. There are people like Dusa and Heindt who've actually made some progress analyzing it. It's basically a problem in combinatorics to know what are the interesting numbers. Because you wouldn't think that out of this numerical condition you'd find the Fibonacci numbers, for example. Mm-hmm. And in fact, some of the things of the sequence of the staircase, you find it adds up to counting numbers of integer points in triangles. And we found some triangles, it turns out, that the combinatorialists didn't know. So it's an interesting set of numbers, and it's very hard to know how to analyze it. And in fact, when I did this problem with Felix, we didn't look at it this way. But it's equivalent to this problem.
OK, another question? Maybe a more difficult question. Sometimes one hears that Floer homology theory is not rigorous. It's not completely...
Well, it depends in which context you're talking about. I mean, the thing is that people have developed a lot of ideas about the algebraic structure and the kind of operations you should be able to have on, I mean, if you're measuring curves of particular kinds. And the people who've been doing that kind of analysis have got ahead of the pure analysts who are trying to, or the people who are trying to get the foundations and make sure things are absolutely proven and are correct. It's converging, but in many situations it's fully proven, I would say. But in some situations there's still room for improvement as far as the proofs go.
Okay, thank you. Any more questions? Let's thank the speaker again, please.